Hello, my name is Jan Gerken, and in this talk I will present this project on emergent equivariance in deep ensembles, which I did in collaboration with Pan Kessel. In this project we investigated the equivariance properties of deep ensembles trained with data augmentation. In order to set the scene, let me start by explaining what equivariance is. Consider this problem of predicting the positions of the red blood cells in this image of cells. If I rotate this image, then the positions of the red blood cells rotate with it, and hence this problem is symmetric with respect to the rotations. Let's now consider what happens if I use a neural network to predict the positions of the red blood cells. Then the output of the rotated input images should be rotated versions of each other. This property, that a transformation of the input leads to a corresponding transformation of the output, is known as equivariance. The problem of constructing neural networks which are manifestly guaranteed to satisfy this property is probably the most prominent aspect of geometric deep learning. However, if you ask practitioners what they would do in such a situation, they would most likely tell you that they would use data augmentation. In data augmentation, instead of training on just one training sample, you also train on transformed versions of that sample, in this case on rotated versions. This strategy has two main advantages. Firstly, it is easy to implement, and secondly, it does not require any specialized architecture, which might be slower than standard architectures, or maybe not even available for the kind of transformation you are interested in. On the other hand, since data augmentation just learns the symmetry properties of the problem, it does not result in exact equivariance, and in particular, away from the training data, the network will in general not be equivariant. Let me illustrate this with a toy example. Here I want to consider the problem of learning the cosine function in one dimension. The cosine is an even function, so it has a flip symmetry around the x equals 0 axis. Let us now use an MLP to learn this function. Here you can see what a typical MLP at initialization might look like. Note that this is not an even function. When I flip it over, you can clearly see that it is not symmetric. Let us now start to train this network with data augmentation. This is what the MLP looks like after I've trained it for one step on this training point at 3 and its mirror image at -3. Note that the MLP became even more asymmetric, although the training data was perfectly symmetric. After the next training step, this effect persists, and you can see that this gets stronger and stronger. If I now jump to the end of training after 2000 steps, the MLP has learned the cosine function reasonably well. However, if I flip it over, you can see that there is a considerable deviation from the symmetry for values roughly smaller than 3. So in this project, we investigated how ensembles react to data augmentation, and in particular if they show the same shortcomings that we just discussed. And the main conclusion from our work is that deep ensembles trained with data augmentation are in fact equivariant. We can prove the exact equivariance of the deep ensembles rigorously for the case of full data augmentation, that is, the samples are augmented with all possible transformations, infinite ensembles, and at infinite width, that is, in the limit where the number of channels in each layer goes to infinity. Surprisingly, this exact equivariance holds for all training times and away from the data distribution. And let me add that although the proof needs these rather strong assumptions, we show with some bounds that you can find in the paper and experimentally that this equivariance property still holds with high accuracy for finite ensembles of finite width trained with only partial data augmentation. Now, in particular, the last 2 points that I mentioned, namely that the equivariance holds for all training times and away from the data distribution, sound unintuitive. I think it's not very surprising that the ensembles which outperform individual models will also show a higher degree of equivariance, but this will only be true after training and only on the data manifold. So how can this be true? The key insight here is that at infinite width, the mean output at initialization is 0 everywhere. If you now start training this ensemble with full data augmentation, the changes you're going to do to the mean will also be completely symmetric. And therefore, the mean output will also be completely symmetric everywhere and hence an equivariant function. Let's see this explicitly in our toy example of the cosine function. Here I plotted an ensemble of 20 MLPs and its ensemble mean in red. As you can see, the mean is almost perfectly 0 everywhere. And mind you, this is of course for a finite ensemble of finite width networks. Let's now consider what happens after one step of training with data augmentation. As you can see, since the update is symmetric, the mean function is also changed in a symmetric way. And this persists over all training steps. At the end of training, we get a function which is almost perfectly symmetric, as you can see if I flip it over. Note that this is even though the ensemble hasn't learned the cosine function very well for values larger than 2. Let me now give you a rough idea of how the proof works. The central quantity we are interested in is the mean prediction of the deep ensemble. It is computed by considering the output of n neural networks after training time t on some test point x. We then take the mean over these predictions. Consider now the limit of infinite ensemble members. Then the mean converges to the expectation value, so we obtain the expectation value over initializations of the output of the trained network. This quantity we want to call mu. Now, in a seminal paper by Jacot et al., it was shown that at infinite width, this mean prediction is given in terms of the neural tangent kernel by this equation. I don't want to go through the equation in detail, but rather give you an idea of what the quantities are that enter it. First, we have, of course, the NTK. Then we have the trained data and the learning rate. And Y are the training labels. The main idea of the proof is now the following. Since we have the training data and labels enter this equation explicitly, we can replace them by their augmented versions. Then we can evaluate mu at a transform point and see what happens. In the paper, we then prove some theorems which imply that for augmented data, one can pull the group transformation through and move it all the way to the right. But now it lands next to the labels y. Here, let us consider an invariant task for simplicity. In the paper, we show the result also for equivariant problems. For an invariant task, the labels are invariant under the transformation due to data augmentation. Therefore, the row of G goes away. And we are left with the untransformed mu, so what we have shown is that mu is indeed invariant. And this argument is independent of t and x and is therefore valid throughout training and in the entire input space. Next, I will show some of the experiments we performed which demonstrate that the effect we claim can be seen in real neural networks. As a first experiment, I want to discuss the Ising model. This is a model from solid-state physics where we consider a 2D lattice of spins which can be either up or down. This spin configuration is mapped to an energy by the Ising model. Let's now rotate this lattice 4 times by 90 degrees. I've rotated the lattice sides here, but not the directions of the spins. So if I consider the first 2 rows of spins here, they are rotated to the first 2 columns here, and the last 2 rows here, and the last 2 columns here. Now, the Ising model is invariant with respect to these rotations of the lattice. That is, all these configurations lead to the same energy. But of course, if I train a generic neural network on this task, it will in general predict 4 different energies for the 4 configurations. So we want to measure how invariant the model is with respect to rotations. To do this, we compute the relative standard deviation, that is, the standard deviation normalized to the mean, over these 4 predicted energies. We call this the relative orbit standard deviation. If this quantity is close to 1, the fluctuations are as large as the mean, and we say that the model is not invariant. Let's now look at the results out of distribution to see how invariant the ensembles are away from the training data. As we saw in the theoretical part, the NTK is exactly invariant, so the relative orbit standard deviation is 0. Here I've plotted the results for ensembles of networks of different width. The shaded regions are the standard deviation over the ensembles, and the solid line is the mean of the metric over ensemble members. As you can see, they are very well compatible with 1, meaning that the ensemble members are not invariant. However, if I plot the ensemble means in dashed here, then the values are much closer to 0, so to perfect invariance. Let's now zoom in to these ensemble means. As you can see, the invariance gets better and better as we increase the ensemble size as predicted by our theory. We can also see that with growing network width, we become more invariant and hence closer to the NTK result as expected. Next, I want to consider a real-world example of histological slices. These slices are classified into 9 classes depending on if they show normal tissue or cancerous tissue. So this one here, for instance, is in class 6. Again, we consider 4 rotations of this sample, and of course this does not change the classification. However, if we train a neural network, we might of course get different classifications. In order to measure how invariant the model is, we take the unrotated prediction as the reference and count how many predictions in the orbit agree with it. So in this case, this orbit same predictions, as we call it, would be 3. Of course, perfect invariance corresponds to an orbit same prediction score of 4. Let us now again consider the out of distribution results. This time we plot the invariance versus training epoch with ensemble size of 5. We performed this experiment 4 times with augmentations by different degrees, so the dashed lines correspond to perfect invariance for the corresponding configuration. These bands show the invariance of the ensemble members. As you can see, there is a considerable spread in particular towards the larger symmetry groups at the top. If we now look at the ensemble means, we can see that they are towards the top of the bands, that is, the means are more invariant than the ensemble members. Mind you, this is out of distribution with an ensemble size of only 5. If we go to ensemble size 20, the effect becomes much stronger and we see it throughout training. As the final experimental result I want to show in this talk, I want to discuss a comparison to other equivariance methods we performed. Here we trained models on rotated versions of Fashion MNIST. Then we computed the orbit same predictions out of distribution for ensembles trained with data augmentation, only data augmentation, E2 CNNs, which are manifestly equivariant models with a specialized architecture, and finally canonicalization, which is a method to make models exactly equivariant with the help of an additional manifestly equivariant model. For C4, that is rotations by 90 degrees, the manifestly equivariant models are of course perfectly equivariant. But as we go to higher groups, the manifestly equivariant models start to suffer from interpolation effects, and the ensembles are as equivariant as the models based on specialized architectures. With that, let me come to the key takeaways from this talk. The way I think about it, there are 2 practically relevant conclusions here. Firstly, if you need ensembles, for example, because you need to do uncertainty estimation or to boost the performance of your base model, then it is a good idea to use data augmentation to obtain an equivariant model, and you probably don't need to use an ensemble of manifestly equivariant models. On the other hand, if you need data augmentation, for example because there is no manifestly equivariant model available for the symmetry transformations that you want to consider, then using an ensemble will not only boost the performance of your base model, but also the equivariance gain due to data augmentation. This brings me to the end of my talk. Thank you very much for your attention, and we would be very happy to discuss with you at our poster number 817 at ICML 2024. You can also find the link to the paper in the description to this video. Thank you.